Hello everybody, this is Elahe Barati, the second year PhD student in Computer Science at Wayne State University. My research area is mainly deep learning with focus on face recognition. Today, I'm going to talk about deadline budget constraint scheduling. This is based on the paper Low Time Complexity, Budget Deadline Constraint Workflow Scheduling and Heterogeneous Resources. This paper has been written by Hamid Arabnejad, George Barbosa, and Radu Portland, and has been published in Future Generation Computer Systems Journal in 2016. This presentation will be started by introduction. I will continue my presentation by defining the problem and introducing the proposed algorithm. The experimental result will be provided after that, and I will finish my presentation by conclusions and future work. But what is utility computing? Utility computing is a service provisioning model that provides some facilities. First of all, it provides computing resources, also infrastructure management to consumers as they need them, and a payment model that charges for usage. There are different environments like service-oriented grid and cloud computing that are the basis for providing these services, but these services is moving toward a pay-as-you-go model. But what is pay-as-you-go model? We all know that computational resources or services have different prices with different performance and quality of services. So users consume services and resources when they need them, and they want to pay when they are using them, and this is called pay-as-you-go model. Based on these things, cost and time become two of the most relevant user concerns. Therefore, there is a challenge between cost and time. As in fact, there is a trade-off between cost and time when we are working on scheduling workflow applications. What is scheduling? Scheduling consists of defining an assignment and mapping of workflow tasks onto resources. We know that scheduling problems belong to the class of problems known as NP-complete. It's very hard to work with scheduling problems. Research on workflow quality of service aware scheduling can be divided to different approaches. The first approach is called single objective approach. In the single objective approach, one quality of service parameter is optimized. For example, time, and constraint will be on another quality of service parameters like cost. But in bi-objective approach, optimizing will be on two quality of service parameters such as time and cost that is done simultaneously, and constraints are related to the processor availability and load. Besides them, we are going to do workflow scheduling on multiple quality of service parameters. So for multi-objective scheduling algorithms, there are different methods and approaches, but two of them are very important: meta-heuristic methods and search-based strategies. But both of them need significantly high planning costs in terms of the time consumed to produce good results. Therefore, we can introduce an algorithm which is called deadline budget constraint scheduling. And in this type of scheduling, constraints will be on two quality of service parameters like time and cost. The objective of this algorithm is finding a feasible schedule map that satisfies the user-defined deadline and budget constraint values. This algorithm is implementing a mechanism to control the time and cost consumptions by each task when producing a scheduled solution. Before going to the algorithm, I'm going to define the problem. And for problem definition, we have different categories. The first category is system model, second one is application model, and the last one is scheduling problem. In the system model, the target utility computing should be introduced. The target utility computing platform is a set of heterogeneous resources that provide services for different capabilities and costs. We're going to define the processor price. Processor price is defined based on the most powerful processor. The most powerful processor has the highest cost, and the less powerful processors has the lowest cost. In the utility grid, the resource price is defined and charged per time unit, but in some environment like a cloud environment, for example Amazon EC2, they are charging per hour. It means that for using just one resource for a few time, we should pay for 1 hour. Therefore, no cost benefit of adding resources for workflow that run for less than an hour. As I said, we're going to use a resource just for 10 minutes, but we have to pay for 1 hour because there is no limitation for there is a limitation for 1 hour in charging. In this paper, a heterogeneous resource has a set of processors available, and each processor has a price per time unit. A typical workflow application can be represented by a DAG or directed acyclic graph, and this graph contains 3 parts. The first part is called T, in which tasks of workflow, for example, we have n tasks, we can show it with a set of T1, T2 to Tn. It also contains data dependencies, which is the edges of the tasks or edges in the graph, and data is a n by n communication, n by n matrix that shows the communication of data. So based on this definition, we can define the average communication time between the task Ti and task Tj, and it can be shown by the average latency plus the ratio of the amount of data that must be transferred from task Ti to task Tj over average bandwidth among all processor pairs. Due to heterogeneity, each task may have different execution time on each processor, so we can define the average execution time of task Ti. So we can have the sum of execution time to complete task Ti on processor Tj over the number of available processors. So because, for example, we have n processors, but we can just use T processors between them. So we can say that P is the number of resources in processor set P that are available. So the earliest start time of the task Ti on processor Pj can be defined by the maximum of 2 elements. The first element is the earliest time when processor Pj is available, and the second one is maximum of the finishing time of task parent plus the communication time between task parent and task Ti, and we compute all of the parents of Ti and find the maximum time between all of them, and among this part and the earliest time at processor Pj, we will select one of them as the earliest start time of task Ti on the processor Pj. We also should know that for entry task, I mean the task that is the first task, earliest start time is 0, and also for the communication time between task parent and Ti, if task parent and task child, both of them are assigned to the same processor, so the communication time between task parent and task Ti will be 0. Earliest finish time can be defined based on the early start time of task Ti and processor Pj plus the execution time on task Ti on the processor Pj. So financial cost can be computed through the cost of running task Ti on processor Pj plus cost of transferring the data required for task Ti and the data storage cost of task Ti. So we can say that the cost of running task Ti on processor Pj can be computed through the execution time of task Ti on processor Pj multiplied by the price of Pj. And based on these values, we can compute total cost, and total cost is the sum of assigned cost of task Ti. But what is it, assigned cost? Assigned cost means the cost of Ti that cost of Ti on the processor Pj that we have selected Pj as its processor. So for a scheduling problem, there are some constraints. The first one will be processor constraint. In fact, there is no processor executes more than one task at the same time. And for predecessor constraint, age shows these constraints. And for budget constraint, we know that the assigned cost, the sum of assigned cost, or we can say the total cost of the project or of the workflow is less than the budget that we have. And for deadline constraint, the length of scheduling cannot be more than the deadline that we have defined. So based on the definition, we can define the deadline budget constraint scheduling algorithm that contains two parts. The first part is task selection and the second part is processor selection. In the task selection, we define the tasks, and in the processor selection, we assign the processor to the tasks. But before going through the algorithm, we have to be sure that there is a possible schedule map for us. So if the budget of the user is less than the cheapest cost, it means that there is no money to be used for a schedule map. So we cannot find any schedule map. But if the budget of the user is more than the cheapest cost, we can subtract them from each other and define the delta cost, which is the spare value. By defining the spare value, we should compute the upward rank, which is the length of the longest path from task Ti to the exit node, and it can be computed through the average of execution time for task Ti plus the maximum of communication time between task Ti and task Tj plus the rank of rank U for task child. So it shows that we can start this computing rank from the exit node and come back to our current node, and it shows the recursive function. But before going through the processor selection, we should define a set which is called p-admissible, and this is the set of available processors that we can use for assigning them to the tasks. And the processors filtered based on an assumption: maximum available budget for the current task that can be consumed by its assignment. By defining this group, we can select from processors from this group. But after computing upward rank, we should compute subdeadline value for each task. And subdeadline value is computed from the minimum of the deadline value for task child minus the communication time between the current task and child, and the execution time, minimum execution time of task child. After computing these values, so we have tasks, but while there is an unscheduled task, we should select the current task and assign the processor to the task. The current task is the next ready task with the highest rank U value. So we select a task and we should compute the quality measure for the processor and task. And the quality measure for all the available processors, we will compute the quality measure value. Quality measure value is the sum of the time quality factor and cost quality factor weighted by a ratio of the cheapest cost execution for unscheduled tasks over the unconstrained budget. So the effectiveness of the cost quality factor can be controlled. The time quality factor defines how much the finish time of the current task is closer to the task subdeadline, and the cost quality factor defines how much the actual cost on PJ is less than the cost on processor that results in the earlier finish time. But the fraction that we talked about it before shows the effectiveness of the cost quality factor, and the higher value of the fraction means that the unconsumed budget is closer to the cheapest cost. Therefore, the cost factor is more predominant in the processor quality measure, and the lower value means the higher difference between the unconsumed budget and cheapest cost. Therefore, the cost factor is less influential, and we can select more expensive processors that generate a lower processing time. By calculating the quality measure, we can select our processor. Processor PJ with the highest quality measure will be selected as our suitable processor. And after that, we will assign the current task to the processor PJ, and we should update our delta cost, which is the minus of delta cost minus the cost of the current time minus the minimum cost of the current time. And by completing this while loop until there is no unscheduled task, we can find the schedule map. For the time complexity, we can define that upward rank and subdeadline subdeadline value have the time complexity of n by p, where p is the number of available resources and n is the number of tasks in the workflow application. And also there is a while and for loop here, and there is ONP for calculating the finishing time and cost for the current task among all the processors. Also for calculating quality measure, we need OP. So the total time will be NP plus P by N, because there is N tasks that we are working on there. For experimental result, they have worked with two different structures. One of them is randomly generated and the other one is real-world application. In randomly generated workflow, they defined around 10,000 workflows or different DAGs. And for simulation platform, they use the SimGrid toolkit, which provides the required fundamental abstractions for discrete event simulation of parallel applications in distributed environments. And they use three different sites. RENES sites, which has normal distribution of CPU power among all its clusters. Sufyan site, which contains a higher number of low-speed processors, and Lille site has a higher number of fast processors. And also they define budget and deadline constraints, and they computed the minimum and maximum execution maximum time, which is the lowest and highest execution time of the application, and they can be computed through the maximum and minimum execution time for each task on the fastest and slowest processor among all the sites, plus the communication time between the parent, which is in the critical path, and the task Ti, and they define the deadline of user and budget of the user based on the minimum time plus an alpha with D and alpha of B, which are in the range of 0 to 1. And the performance metric, which is called planning successful rate, and it's the percentage of validated schedules, can be computed through the ratio of successful planning over the total number in experiment. And based on the experiment on randomly generated workflow, we can see that the result is comparable to the other state-of-the-art methods, and they could get a good result in lower time. And we can see that they could find the schedule map in the less time than the other methods. Also, the results for real-world application shows that their method somehow is better than BHEFT method, and it's comparable to DCA, and also better than GA in most of the time. So based on this this algorithm, we can see that the DBCS algorithm was presented for budget and deadline constraint scheduling, and it achieves a similar performance to higher time complexity algorithm with the time complexity of the heuristic algorithm, I mean ON2 for N tasks and P processors. In the future work, they're going to extend their algorithm to consider the dynamic concurrent tag scheduling problem, which allows users to execute concurrent workflows that might not be able to start together but can share resources. And thank you for listening to my presentation.